Welcome to all in the new lecture. So here in this lecture we will discuss about the eigenvalues and eigenvectors. So first of all, what is the eigenvalues and eigenvectors? Here we take an n cross n matrix. So we say that that is the A matrix. So if we introduce a scalar quantity lambda in this, so it is called the eigenvalue. Lambda is called here the eigenvalue of matrix A. When if there exists a non-zero vector x in R such that Ax is equal to lambda x. So here our lambda is represent the eigenvalue of the matrix and x is the eigenvector of the matrix corresponding to the eigenvalue lambda. Now, how to compute the eigenvalues and eigenvectors of any matrix? So, first of all, we have a n cross n matrix and we take the eigenvalue is lambda, then the corresponding eigenvector is x. So, we can say that Ax is equal to lambda x. So, our equation, we can write this equation like that Ax minus lambda x is equal to 0. And again, we can write this is like that A minus lambda, if we take x eigenvector is common. So A minus lambda in x is equal to 0. What is this in? Actually, this is the identity matrix. Why we introduce here identity matrix? Since we have A is a R matrix, x is x is a vector, means vector means we have again a matrix, but lambda is only a scalar quantity. So and here we subtract lambda from this matrix. So we need here the matrix for subtraction of this. So here we use the identity matrix. So we can use identity matrix with any scalar if we want the addition and subtraction from any matrix. So we can write this A minus lambda I. Here we take that identity matrix, that order identity matrix, which order we have the matrix A. Now we solve this equation A minus lambda I determinant is equal to 0. So here we have this matrix, so we can take the determinant of this, and if we put this determinant is equal to 0, so this is called the characteristic equation. And from this, when we expand this determinant, so from expanding of this determinant for solving of this determinant, we get a polynomial in lambda, because lambda we have an scalar quantity. So in lambda we get a polynomial that is called the characteristic polynomial or eigen. Here we have the polynomial of the matrix, characteristic polynomial of matrix. Now suppose we had take an example here, 2 by 2 matrix. We have A matrix and find the eigenvalues and eigenvectors of this matrix. So what is our first thing? First thing is that we have to make the we have to solve the characteristic equation. And what is the characteristic equation? So we form our characteristic equation when we use A minus lambda I. So and here we take the order 2 identity matrix, because our A matrix is the 2 order. So now we first solve it A minus lambda I2. So this is our A matrix minus lambda. This is our identity matrix. When we subtract from this, so we will get minus 4 minus lambda minus 6, 3, 5 minus lambda. Now we solve the characteristic equation. So for the characteristic equation, we take the determinant of this. So when we take the determinant of this, so we can expand this and we can expand this. So how to solve the determinant? You know that is very well. So by the cross multiplication, we can solve this determinant. So we get this lambda square minus lambda minus 2. Now what is our characteristic equation? That is A minus lambda is equal to 0. So we put this is equal to 0, and from here we have this quadratic equation. So we can get here the values of lambda. So when we solve it, we get the lambda is equal to 2 or minus 1. So now our eigenvalues, because I told you that lambda is represent the eigenvalues of the matrix. So our eigenvalues of this matrix A is here 2 and minus 1. Now next, these are the eigenvalues. Now we need to find the eigenvectors. So now we find the corresponding eigenvectors of both of these eigenvalues 2 and minus 1, and we use here a minus lambda I x is equal to 0. So through this equation we find out the eigenvector for each corresponding value of eigenvalue. So now first of all we take here one by one our eigenvalues. So first we take for lambda is equal to 2. So first we find the eigenvector corresponding to lambda is equal to 2. So now we use here the equation a minus 2 I x is equal to 0. So in place of lambda we put here 2. So now what is our equation? Our equation is become that our matrix is a minus 2i, and here this matrix is become like that minus 6 minus 6 3 3. So we get this matrix when we subtract when we subtract 2 on the all diagonal elements from the matrix A. Now after that, we need to solve these matrices, and here you know that how to solve the system of equations. Same as here we have. So first, it's depend on you. How can you solve it? So first, we can use here the row operations. Means to make suppose 1. So we use R1 and divide it by minus 6 by R1. So we will get this matrix. After that, we can reduce here the one row, so we can use here r2 minus 3 r1, so we get this row is become 0. So now we make here are the equations. So what will our equations? That are x1 plus x2 is equal to 0. So now we can see that here we get only the one equation and we have the two variables. So how can we find the values of these two variables with the one equation? In the last lecture, I told you that if we have the less number of equations from the number of unknowns, so it means that we have the number of solutions, infinite number of solutions. So here in this case, we have to put x2 is anywhere, any scalar quantity, and find where x1 in terms of that scalar quantity. So same procedure we have to follow here. So here our x1 is minus x2. So our equation, if we suppose put here x2 is equal to r, so what is our x1? That become minus r. So now we can say that our eigenvector of A corresponding to lambda is equal to 2. It is the, in vector form we have, vector is our x1 x2. We say that this is our vector v1 corresponding to lambda is equal to 2. So now put here, what is our x1? X1 is our minus 1 and x2 is 1 if with r, right? If we take the r is common, so now our eigenvector is minus 1 1. So this is our the eigenvector corresponding to eigenvalue lambda is equal to 2. Clear? Next, for the next value of lambda is equal to minus 1, we find the our eigenvector. So now we use this a plus I1 x is equal to 0, and so we when we subtract add 1 in diagonal elements of the matrix A, so we will get this type of matrix. And now we solve this. So here we can see easily that these two rows, from these two rows one rows becomes 0. So you use row operations and you know how to very well very well how to use the row operations and reduce the rows. Okay, so when we use these operations, so we get here this r2 becomes 0. So now our equations linear equations become x1 plus 2x2 is equal to 0. Now again we have here the one equation and two unknowns. So again we need to find the solution, to find the vector x1 and x2. So we have to put any x1 or x2 with any scalar quantity. So here we have x1 is equal to minus 2x2. So if we put suppose x2 is equal to s, so our x1 is become minus 2s. So now the eigenvector of the matrix A corresponding to the lambda is equal to minus 1. This is, suppose we say that that is eigenvector v2. So here this is minus 2 and 1 because our x1 is minus 2s and x2 is s. So we take s is common. So now our eigenvector is minus 2 1. So this is our eigenvector corresponding to the eigenvalue -1. So like that we solve we can calculate our eigenvalues and corresponding to the eigenvectors. One more thing you see here that here in when we solve this matrix, so always you have means you can become one row here, always one row becomes 0. Why? Because a minus lambda I, you do here a, do you, if you do this matrix a plus I2 x is equal to 0 and you put here determinant of this is equal to 0, right? You take a plus lambda I2 is equal to 0, determinant a, initially we take determinant a is equal to 0. It means that when we take if our determinant is equal to 0, it means that in that matrix we have at least one row is 0, right? So here always when you solve this matrix, you have always a row becomes 0. So if you can easily use the operations, row operations and reduce the rows, so you can reduce it and always you can find one row becomes 0 and easily you can find the values of x1 and x2 and simplify equations of x1 and x2. Otherwise, it doesn't issue that if you directly form here the equations. So means you have to not take to stress to reduce the matrices. Okay, you just directly find the matrices equations from here minus 3x1 minus 6x2 and second equation is 3x1 plus 6x2. So when you solve these two equations, then again you will get this type of equation, this type of you again get this type of equation. Okay, so if you easily solve it, then you can solve it. Otherwise, you can directly form here with this, you can directly form the equations and solve these two equations. Again, you will get this type of equation, not the other one. Clear? Okay, let's take another example. Here we have a 3 by 3 matrix and find the eigenvalues and eigenvectors. So first thing is that first we make this A minus lambda I3 because we have the 3 by 3 matrix here. So we take identity matrix is order 3. So now first we calculate A minus lambda I3. So it means that we have to subtract lambda from each element of the diagonal elements of this matrix. Now for the characteristic polynomial, we take the modulus determinant of this a minus lambda I determinant. So how to solve this determinant? So now to solve this determinant, you can solve uh, any way, any type of, it's depend on you how you solve this determinant. Okay, directly you can expand any row or any column and solve this determinant and here or you can use the row operations or any column operations to reduce this to solve this determinant. So here what we do here from this to this we use here the row operation r1 plus minus r2. If we use r1 minus r2 so it become we have this type of determinant. After that we have this determinant, so we use here c2 plus c1. If we use c2 plus c1 so we get this type of determinant. Now it easy to calculate to expand this determinant. Why? When we expand it about r1 and in r1 we have only the one non-zero element, all two elements are 0. So easily we can expand it through R1. So now we expand it through R1. So now this is 1 minus lambda and this become 9 minus lambda multiplied 2 minus lambda minus 8. So now when you solve it, you will get this type of polynomial minus lambda minus 10 lambda minus 1 whole square. Now when you solve this characteristic equation, what is the characteristic equation? A minus lambda is equal to 0. So now we put this is equal to 0 and from here we get the lambda values, that is lambda is equal to 10 and 1. And 1, lambda minus 1 ka whole square, it means that we have the value of lambda is 1 means we have the lambda is 10, 1 and 1, right? Two times of ones we have because how many lambda is here? 2. But we have the 3 by 3 matrix, it means that you have three eigenvalues. And what are these three eigenvalues here? 10, 1 and again 1. So 2 times of 1 you have and as 10 you have the eigenvalues. Three eigenvalues are here 10, 1 and 1. And in numerically we can say that eigenvalues are 10 and 1. So now we find the corresponding eigenvectors of all these eigenvalues. So we take a minus lambda ix is equal to 0. First we find the eigenvector corresponding to lambda 1 is equal to 10. So we put here a minus, in place of lambda we put 10. So a minus lambda ix is equal to 0. So now matrix is become like that. Now we can reduce this matrix, so we can reduce it like that, it becomes 0. So how can we become 0? If we apply suppose 5r2 plus 4r1, so our r2 is become like that, and in r3 if we use 5r3 plus 2r1, so it becomes 0. Now after that we see that these, the r2 is minus 918, this is 18 minus 36, so we can reduce it. So if we use here r3 plus 2r2, so now our third row is become 0, right? I told you that one, at least one row should be 0 here. Okay, always be 0, because your determinant a minus lambda I you take is 0. It means that a1 row is always be 0 here. Now you can form the equations here. So it become minus 5x1 plus 4x2 plus 2x3 is equal to 0, and second equation is become minus 9x2 plus 18x3 is equal to 0. Now when you solve these equations, and you can see here you have two equations and three unknowns, always you have the infinite number of solutions. So here you have to assume any one variable scalar quantity. So suppose we assume here x3 is equal to r, then if we put here x3 is equal to r, so our x2 is become 2r, and when we put here x2 and x3 in terms of r, so we get x1, that is 2r. So now our eigenvector of matrix A corresponding to the eigenvalue 10, that are 2, 2, 1, x1, x2, x3. So this is 2, 2, 1, and this is r. So this is r, the eigenvector corresponding to the eigenvalue 10. Clear? Now let's take the eigenvector corresponding to the eigenvalue 1, and here you see that 1 is repeated two times, right? So when we find the eigenvector, so this is a minus lambda ix is equal to 0, we put here our lambda is equal to 1 here. So now our matrix has become like that. When you solve it, you can see that easily. If we use here r2 minus r1, so say r2 is become 0. When we apply r2 r3 minus r1, so our r3 becomes 0. So now we have this type of equations. Here we have on, here we can become two rows become 0. So only one equation we get, that is 4x1 plus 4x2 plus 2x3 is equal to 0. Now you see here. Here we have the only one equations and find the three unknowns. So what we do here? Here we have the now the number of solutions here, and so how can we solve these variable equation values? So we have to put here two variables values, any scalar quantities of two variables. So here we suppose that our x2 x3 is, suppose we take 2t, or x2 is s, because we have to take another scalar quantity. If we take a scalar quantity t and s, and we assume that our x3 is 2t and our x2 is s, then we can solve it by x1, that is minus s minus t. You can solve it. If you put x3 is equal to 2t, so it becomes 4t. So now when you calculate x2 and x2 put is s, so here x1 is minus s minus t. So now what will be the eigenvector of A corresponding to this one? So how can you arrange? So your vector will be x1, x2, x3. What is your x1? Minus s minus t. What is your x2? S. What is your x3? 2t. So now let's see how to make the eigenvectors. Now we separate these parameters s and t. In the last we see that we have only the one scalar quantity, so we get the one eigenvector. Now we have here the two scalar quantities s and t. So now we separate these scalar quantities. So when we take s, means we have to take the coefficients of s only. So what is the coefficient of s here in x1? Minus 1. What is the coefficient of s here? 1. And what is the coefficient of s here? No coefficient of s is here, it means that is 0. plus t. Now we take the coefficient of t. What is the coefficient of t here? -1. And what is the coefficient of t here? No coefficient is here. It means that is 0. And what is the coefficient of t here? 2. It means that our one eigenvector is -102. So now you can see that, and you can say that the eigenvector of A corresponding to lambda is equal to 1. You have the two bases and eigenvector, that is -110 and -102. Why we get here the two eigenvectors? Because lambda is equal to 1, we have the repeated eigenvalues at lambda is equal to 1. So we have the two eigenvalues, so we have the two eigenvectors. We can get the two eigenvectors from here. Okay, so now we have three eigenvalues. So according to that, we have the three eigenvectors should be there. So these are the eigenvalues, eigenvectors corresponding to each eigenvalues. Now, one point is here. If an eigenvalues occurs as a k times repeated root of the characteristic equation, we say that it is of multiplicity k. So what does it mean, multiplicity k? In this example, we see that at lambda equal to 10, what is the multiplicity of lambda equal to 10? The eigenvalue at lambda is equal to 10 has multiplicity 1. Why? Because we have get the eigenvalue, one eigenvalue at lambda equal to 10, and when lambda is equal to 1, we have get the two values of 1, right? It means that the multiplicity of lambda is equal to 1 is 2, right? So we can say that is like that, multiplicity is 2. If eigenvalue is comes one time, so that multiplicity is 1. If eigenvalues comes 2 or 3 times, so according to that, their multiplicity will change. Here eigenvalues, we get the two eigenvalues 1 1, so that we say that the multiplicity of lambda is equal to 1 is 2. If suppose we get lambda is 1 1 1 3 times 1 1 1, it means that we can say that at lambda equal to 1, we has the multiplicity is 3, right? So like that, you solve your eigenvalues and eigenvectors corresponding to the eigenvectors. So now today's lecture is completed now. Thank you.